Hello my dear students, welcome back to a new video. We are going to discuss the section inverse functions and their derivatives from the chapter Transcendental Functions of the textbook Calculus and Analytic Geometry 9th edition by G.B. Thomas and R.L. Finney. See the chapter name Transcendental Functions. What is transcendental functions? We have algebraic functions and transcendental functions. Algebraic functions are functions with the usual algebraic operations of addition, subtraction, multiplication, division, and raising to constant power. For example, we can say polynomial functions are algebraic functions and rational functions. That is, if p of x and q of x are two polynomial functions, then the function of the form p of x by q of x. We have seen many more examples for polynomial functions and rational functions in the chapter Limits and Continuity. Transcendental functions are the functions that are not algebraic. For example, we can say exponential functions, logarithmic functions, trigonometric functions or inverse trigonometric functions, etc. We can discuss inverse functions and their derivatives. Before going to the derivatives, we have to see inverse functions. We all know that a function has an inverse if and only if it is 1, 1. That is, if a function is 1, 1, then it has an inverse. Or if a function has an inverse, then it is 1, 1. So we can just have a look at 1, 1 functions. Before seeing 1, 1 functions, what is a function? If we have two sets x and y, a function from x to a set y assigned to each element of x exactly one element of y. Or we can say a function is a rule that assigns a value from its range to each point in its domain. For example, we can see we have two sets x and y. X is equal to 1, 2, 3, 4. Y is equal to 1, 2, 3, 4. Each element of x should have exactly one element in y. So 1, 2, 3, 4 should have an image and one element can have only one image. For example, we can say 1 we can map to 2, 2 to 3 and 3 to 1. This cannot be a function because 4 has no image. This is not a function. If we map 4 to 1, then this is a function. That is, each element of x has an element in y. This is a function. If we map 4 to 4, we have 4, already have one image. If we map 4 to 4 again, then it is not a function. Because each element of x should have exactly one element in y. Here 4 has two elements in y. So this is not a function. We can see more examples. 1, 1 functions are functions that has a unique image. For example, we can say x is equal to 1, 2, 3, 4. Y is equal to 1, 2, 3, 4. 1 maps to 2, 2 maps to 3, 3 maps to 1. If 4 maps to 1, then it is a function but not 1, 1. Then 3 and 4 has the same image, not a unique image. If 4 maps to 4, then it becomes a 1, 1 function. It's a 1, 1 function. This function is both the 1, 1 and onto. Onto functions are every element of y maps to each element in x. Here every element of y has a pre-image. If we have one more number here 5, then this is a function and 1, 1 but not onto because 5 has no pre-image. We can see the examples in more clear. First example, see x is equal to 1, 2, 3. Y is equal to 1, 2, 3. X, Y. 1 maps to 2, 2 maps to 3, 3 maps to 1. Here this is a function which is both 1 1 and onto. A function because each element of x assigned to exactly one element in y. We can see here f of 1 is equal to 2, f of 2 is equal to 3, f of 3 is equal to 1. This is 1 1 because each element of x has a unique image, and onto because every element of x maps to every element of y, or we can say range and codomain is same. So this is a 1 1 and onto function. Next example, see, x is equal to 1 2 3, y is equal to 1 2 3 4. 1 maps to 2, 2 maps to 3, 3 maps to 1. Here this is a function because each element of x maps to exactly one element in y. This is 1 1 because each element of x has a unique image, but not onto because no element of x maps to 4. So we can say this is a 1 1 function but not onto. See another function, x is equal to 1 2 3 4, y is equal to 1 2 3. 1 maps to 2, 2 maps to 3, 3 maps to 1, and to become a function 4 should maps to some element in y. We can give 4 to 1. Here 3 and 4 assigned to same value. So this is not 1 1, but this is onto because every element of y has a pre-image. So we can say this is onto function but not 1 1. Next example, see, x, y, x is 1 2 3 4 and y is 1 2 3 4. Here 1 maps to 2, 2 maps to 3, 3 maps to 1 and 4 maps to 1. Here see, this is a function because each element maps to exactly one element in y, but not 1 1 and not onto. See here no element maps to 4, so this is not onto. See, f of 3 and f of 4 is equal to 1, that is 3 and 4 maps to same element in y, so this is not 1 1. Not 1 1, not onto, but it is a function, So we have seen 1 1 and onto function, 1 1 but not onto but not 1 1, not 1 1 and not onto. Next we can see example to show not even a function. Take example, x is equal to 1 2 3 4, y is equal to 1 2 3. 1 maps to 2, 2 maps to 3, 3 maps to 1. Here see, this is not a function because every element of x should map to exact one element of y. Here 4 maps to no element. So this is not a function. Another example we can see, x, y, 1 2 3, 1 2 3 4. 1 maps to 2, 2 maps to 3, 3 maps to 1. And we can assign 3 to 4. Here see, each element has an image but not exact. 3 has 1 and 4. So this is not a function. Here we cannot say a rule to assign 3. So this is not a function. Hope you understand the concept of function, 1 1 function and onto functions. Here we need only 1 1 functions. A function is a rule that assigns a value from its range to each point in its domain. Some functions assign same value to more than one point. That is not 1 1. For example, we can say square functions in real life. For example, f of minus 1 is equal to minus 1 square, that is 1, and f of 1 is equal to 1 square, that is 1. That is f of x is equal to x square. This is not 1 1. Like that we can say f of x is equal to sine x. F of x is equal to sine x is not 1 1. For example, we can say sin n pi is equal to 0 for n equal to 0, 1, 2, etc. That is sin 0 is equal to 0, sin pi equal to 0, sin 2 pi is equal to 0, etc. We have same value 0 to more than one element in x. So these are functions that are not one-one. While some other functions never assume a given value more than once. For example, we can say square root and cubes of different numbers are always different. We can say the function f of x is equal to root x. For x greater than or equal to 0, we can take only real values. If we take negative values, root of minus 1 is I, complex numbers. So we can consider only real numbers. Like that, f of x is equal to x cube. F of 1 is equal to 1 cube, that is equal to 1. F of minus 1 is equal to minus 1 cube, that is equal to minus 1. Like that, if we take any two distinctive values, it will have a distinct image or unique image. So a function that has distinctive values at a distinctive points is called a one-one. Or we can say a function f of x is 1 to 1 on a domain D if f of x1 not equal to f of x2 whenever x1 not equal to x2. We can write the definition as a function f of x is 1 to 1 on a domain D if f of x1 not equal to f of x2 whenever x1 not equal to x2. That is, if we have two distinctive pointer x1 and x2. That is x1 not equal to x2, then it has distinct images f of x1 and f of x2. That is, if x1 not equal to x2, then f of x1 not equal to f of x2. If it was not 1, 1, then we can map x1 to f of x1 and x2 to f of x1 itself. If it is 1, 1, we have to map it x1 to f of x1 and x2 to f of x2. Or if we have numbers 1 and 2, then f of 1, its image is f of 1, its image is f of 2. And f of 1 not equal to f of 2. If it is not 1, 1, we can have even f of 1 equal to 1 and f of 2 equal to 1. We can map 1 to 1, 2 to 1. But if it is 1, 1, we cannot map like this. Hope you understand. I am not making you confusion. For example, to 1 function, we can say f of x is equal to root x. Here, whenever x1 not equal to x2, root x1 not equal to root x2. We are defining the domain as non-negative numbers because we know root of minus 1 is I, complex value. We are taking only real values. Now we can say an example for a function that is not 1, 1. See, f of x is equal to sin x is not 1 to 1 on the interval. We are considering the interval closed interval 0 pi. We can directly say sin 0 is equal to sin pi. That is for x1 not equal to x2, that is 0 and pi. We are taking two distinctive values, but its images is same. But f of x1 equal to f of x2. F of 0 equal to 0 and f of pi equal to 0. If we take the open interval 0 pi, then also it is not 1 1. We can see the graph of sin x like this 0 pi 2 pi. We are considering this interval. See, if we take this point x1 and this point x2, what's f of x1 and f of x2? F of x1 is this value and f of x2 is also this value. That is f of x1 equal to f of x2. Same value. This is not 1 1. Or we can write, for example, sin pi by 6 is equal to sin 5 pi by 6. Or sin pi by 6 is equal to sin of pi minus pi by 6. So this is not 1 1. But if we consider the interval 0 to pi by 2, then it is 1 1. Because we know that a sine of angles in the first quadrant are distinctive. Or we can say this is pi by 2, then this is the function. Here no two x has the same value. So the domain is important. In 0 to pi by 2, sin x is equal to is 1 1. Here see, without looking to the values, we can directly say from the graph whether 1 1 or not. Now we can discuss that. The graph of a one-to-one function y equal to f of x can intersect a given horizontal line at most once. We know one-one functions are the functions with the f of x1 not equal to f of x2 whenever x1 not equal to x2. Or we can say f of x1 y1 and f of x2 y2, that is y1 not equal to y2. So if the horizontal line intersects the line more than once, it's assumed the same y value more than once, and it is therefore not one to one. For example, we can see this function. Here, consider this horizontal line. It meets at 2 points. Here, take this point x1, this one x2. x1 and x2 has same image y, we can say. F of x1 is equal to this value and f of x2 is equal to this value. We can see more examples. See the graph of y equal to x cube. We can see the points. When x is equal to 0, y equal to 0. When x is equal to 1, y equal to 1. 1 cube is equal to 1. When x is equal to minus 1, y is equal to minus 1 cube minus 1. When x is equal to 2, y cube is equal to 8. When x is equal to minus 2, y cube is equal to minus 8. See the graph. 1, 2, minus 1, minus 2. Here 2, 4, 6, 8. 2, 4, 6, 8. Here minus 2, minus 4, minus 6, minus 8. When x is equal to 0, 0. When x is equal to 1, y equal to 1. When x is equal to 2, y equal to 8. When x is equal to minus 1, y equal to minus 1. When x is equal to minus 2, y equal to minus 8. So this graph is like this. So if we take any arbitrary horizontal line, it meets at most once. See here, at most once. So we can say this is one-to-one function. Next example, see y equal to root x for x greater than or equal to 0. See when x is equal to 0, y equal to 0. When x equal to 1, y equal to 1. When x equal to 4, y equal to 2. When x is equal to 16, y equal to 4. So these are the points. We can draw the graph. 2, 4, 6, 8, 10, 12, 14, 16. And y-axis 1, 2, 3, 4. So 0, 0, 1, 1, 4, 2, and 16, 4. So the graph is like this. I'm making a rough sketch only. Here also, if we take any horizontal line, it means at most once. So this function is also 1, 1. Do you have any doubt how y equal to root x become a function? See, what is the value of root 1? Is root 1 is equal to plus or minus 1? Then one element of x maps to two elements in y, that is plus 1 and minus 1. Then it cannot be a function. So we are considering only principal square root, that is non-negative square roots. Next we can see the graph of y equal to x square. Y equal to x square. Then the points are 0, 0, 0 square is 0, 1 square is 1, minus 1 square is 1, 2 square is 4, and minus 2 square is plus 4. Then the graph is, you can take the values 0, 1, 2, minus 1, minus 2, 1, 2, 3, 4, 1, not needed, 1, 2, 3, 4. So the points are 0, 0, 1, 1, minus 1, 1, 2, 4, minus 2, 4. So the graph is like, here see, consider a horizontal line on the positive y-axis. Say this. then it meets at 2 points, here and here. So it cannot be 1 1. We already know that y equal to x square is not 1 1, because minus 1 and 1 maps to same value 1. Like that, negative numbers and positive numbers maps to the same value. So this is not 1 1. Next, consider the graph of y equal to sin x. We know the graph. We can consider the interval 0 to pi. 0 pi, the graph will be like this. This is 1. Here we can draw the points pi by 6, 5 pi by 6, like that. Then if we consider a horizontal line, see, it meets at a 2 point. So it is also not 1 1. So in case of y equal to x cube and y equal to root x, graph meets each horizontal line at most once. Here, see, here the horizontal line does not meet anywhere, but that's not a problem, at most once. But in the case of y equal to x square and y equal to sin x, one or more horizontal lines meet more than once. See here, this horizontal line does not meet anywhere, but we should get at least one horizontal line that meets at 2 points or more, 2 or more points. So we have to consider all the horizontal line. If there exists one horizontal line that meets at 2 points, then it is not 1 1. If all the horizontal lines meet at most 1 point, then it is 1 1. So we can say a function y equal to f of x is 1 to 1 if and only if its graph intersects each horizontal line at most once. This is called the horizontal line test. So the horizontal line test is a function y equal to f of x is 1 to 1 if and only if its graph intersects each horizontal line at most once. Now we can solve some simple exercise using the horizontal line test. Exercise: identifying one-to-one function graphically. Which of the function graphed in the following exercise are one-to-one and which are not? Here 6 graphs are given. We can check which is 1-1 and which is not. The horizontal line test is a function is 1 to 1 if and only if its graph intersects each horizontal line at most once. Here in the first case, all the horizontal line. If we take any horizontal lines, it meets the graph at exactly 1 point. So this is a 1 1. Or we can say it passes the horizontal line test. Or each horizontal line meets at most once. See the second question. Graph of y equal to x raised to 4 minus x square. Here the horizontal line meets the graph at least 2. Here on the positive y-axis it meets exactly 2 points, and between minus 1 and 0 it meets at 4 points. See, if there exists at least one horizontal line that meets the graph more than once, then it is not 1 1. So we can say second question, y equal to x raised to 4 minus x square is not 1 1. Next, third question, see, y equal to tan x. Here each horizontal line meets many points, more than once, therefore it is not 1 1. We have to show any one horizontal line. Next, see the fourth question, the greatest integer function. Here, if we take any line, see this horizontal line, it meets till here. The horizontal line meets the graph at many points here. See, this much points the horizontal line will meet. So it is not 1 1. Next, see the graph of y equal to 1 by x. Here see, this is 1 1. If we take any horizontal line, in the positive y-axis, it meets at 1 point. If we take in the negative y-axis, it meets at most 1. If we take the x-axis, that is y equal to 0, here it meets at no points. That's not a problem, at most 1 point here. So this is a 1 function. Like that, y equal to x raised to 1 by 3. See, if we take any horizontal line, it meets only at 1 point or at most 1 point. So it is also 1 1. Y equal to minus 3x cube, first question. And fifth question, y equal to 1 by x. Sixth question, y equal to x raised to 1 by 3 are 1 1 here. And second, third, and fourth are not 1 1. So this is all about 1 1 functions that we need for this chapter. We can discuss inverses in the next video. If you find this video useful, please like, share, comment, and subscribe to our channel. Thank you for watching. Thank you.